Again, welcome to Physics 4B. Today is Thursday, May 20th, and today is lab. The lab is actually two labs at the same time. So what I'm doing now, excuse me, trying to pull the labs first, the instructions on the labs. And here they are, and they're in Unit 13. Okay, that's not it, that's the discussion. Yeah, they're actually in Unit 13. I put the wrong link, that's all. Okay, so as usual, there are two files in there for this lab. There is the usual file, the PDF file, which gives you the instructions and everything else. And there is also, in addition to it, a jar file, which is the Java file. So I'm expecting that you guys have had already figured it out on how to do the Java file, namely on your computer, and that you have Java installed and the runtime Java, at least, that is installed. If not, refer to the lab that was a few weeks ago. And that should be the same stuff in here for the Java. Once you have that, you have to enable it so that it opens files from here. Once you do that, this lab, you're going to do the simulation. If you're into some difficulties, please let me know, and then hopefully we can figure it out a solution for it. Once you're done with this lab, then you have two options, really. Option one is to uninstall Java completely from your computer, which is probably an option too, because most of the times you're not going to be needing it actually on a daily basis unless you're doing programming or games actually on stuff like that, because it does a lot of simulations and have a standalone basically environment for itself. Because it had vulnerability in the past, namely that people exploited some of its features to basically deliver things that are unwanted, that's basically the precaution that I'm asking you to take. Either remove it completely or secure it back again so that it doesn't open unless it's trusted source, in which case it's going to be safe on your computer. So this is the only thing I'm going to mention about the Java stuff, okay? So we will be done completely after today with it. There is a few simulations that we will need to do from there. So I'm going to download the instructions first and open it with Adobe. And then also download the Java because I need that too. Okay, it's telling me to save it. Since I saved it last time and I really don't want to save it several times now, so I'm going to go to the folder where I saved it last time and open it from there. So I'm going to open the file. When I double click on it, because I already enabled the security feature so that it allows me to do that. So let me go back in here and let me share with you the instructions for the lab. So the lab instructions first. Before I do that, let me make sure it's sitting on the correct screen, because I don't want it to be sitting on the wrong screen. Okay, so let me go back in here, share the lab instructions. Okay. So this is the instruction for the lab, and it's no different than any other lab we've been dealing with. Basically, the first thing that you have to do is write your name, go through the lab, understand what the lab is about. The lab is about the RL circuit and the RLC circuits. Okay, those are the two, basically, both of them. Now, for the RL circuits, we're going to have basically a steady source of current, namely DC battery, normal battery. For the RLC circuit, also, the first part of it is going to be also a DC battery, namely a regular battery. And then the second part is going to give you a simulated data for an AC battery. So that is basically in a nutshell what the lab setup is. So this is the RL circuit, namely I have a resistor and an inductor with a power source in here. The way that it looks like, it's square power, and this square power is that sometimes it's basically on and sometimes is off, or sometimes positive and sometimes negative. As this is actually what it is. So sometimes it's pushing current this way, sometimes other times it's pushing it in the opposite direction, and that's the end of it. So now trying to build a current inside the circuit. And this, we did it in way back in chapter 29, I believe. And where we did the basically building up a current inside the circuit where there's an inductor. current running through an inductor. So once you solve this equation, you're going to find that depending on the initial conditions, we did it without the initial conditions. There was no initial current in the circuit. But because of this situation here, at some point you're pushing current in one direction. Let's say, for example, it's going this way. Okay, so you have a current going this way, and then the signal flips. It's going to be pushing it in the opposite direction. So at that point, when it flips, there is a current already existing from the first stage, from this point. Okay, that's why the problem has to be changed slightly. Because when we did it, we started with no current, at least in the lecture, and we had a solution without the I naught. Actually, without the I naught is exactly what we had in our classroom when we did this one together. Now the problem shifted a little bit so that you have an initial current in the circuit, and that initial current is because you're solving it for each cycle. And this is periodic, it's repeating forever and ever and ever and ever and ever. So for any given cycle, you already have a current from the previous stage. So even though you exhaust this one in here, namely you build the current in here, in other words, there was a current going this way. So when you try to push it this way, you go through the stages, first of all, lowering it down, and then it's going to be moving this way. By the time you reach this point, again, the signal is going to flip again, so that you're pushing the current this way. So again, that becomes initial condition for the next cycle. So that's basically what this expression is. It's similar to the lecture with the exception that you have the I naught in here added to it. Obviously, V across the resistor is just you have to multiply by the resistance, multiplying by this entire expression. And if you solve for it, this is how it's going to look like, okay? Here is the first question. The first question is verify that equation 1 or equation 2 is a solution to equation 1, basically. So let me stop sharing the screen and show you how that is done. So stop share, and let me put my notes in here. And I'm in the Tuesday group. And this discussion is about the lab. So I'm gonna come in here and share the screen again and bring my pen. And this is for the lab, of course. So what we're saying in here, we want to verify that I sub t equals to epsilon over R plus I naught minus epsilon over R times the exponential of negative t over tau. And tau, you see that it's L over R, so it's minus RT over L, basically. Let's put it this way so that we're straight out. So in this case, we want to verify that L di over dt plus Ri is indeed equal to epsilon. That is the question that we're asked, really, because we want to verify this is true, if this is a solution. So what we do in this case, we take this expression multiplied by R, and we have the second term. So this times R will give me, R cancels R, so it gives me epsilon plus, again, R times I naught is going to give me Ri naught, minus, again, the R cancels the R, so it's going to be epsilon exponential of negative RT over L. So this term is easy. It's this term exactly gives me these parentheses. Now I have to do the derivative and find the second term. So the derivative in here of this expression, so multiplying by L, of course, when we're done with it. So the derivative drops this factor. So this becomes, because this is constant, so the derivative of di with respect to t is going to be 0 plus, or negative in this case, because of the fact that I have a negative sign in there. So it's going to be a negative R over L times I naught minus epsilon divided by R times the exponential of negative t RT over L. So now I have to multiply by this L. So the L times the negative R over L becomes just negative R. That's it, because the L cancels this L. And I will be left with I naught minus epsilon over R exponential of negative RT over L. Now, so this is added. Is it equal, and that's the question, to epsilon? So let's look at it term by term. First of all, I have a positive Ri naught, and I have a negative Ri naught times the exponential. Both of them are multiplying the exponential, so this and that they cancel. This one is positive, this one is negative. I have a negative times negative, that's a positive. Epsilon over R times R, that is epsilon times the exponential. And I have a negative epsilon times the exponential. They have also the right signs to cancel, because this is positive and they have the exact same term. So the only thing that is left on this side is epsilon. And is epsilon equal to epsilon? Obviously, yes. So it checks. So that is really the proof that indeed that is a solution. That 2 is a solution to equation 1, really. So let me go back to the RLC circuit and move this out of the way. So that was the question 1. So I hope that you follow it and you just do it. So it's just taking the derivative. Now comes this part. This is the one that requires the Java. So what I'm going to do now is I'm going to switch to a screen to the Java that I have opened, the Java file that I have opened, and basically do the same steps in here as this is asking me to do. So share now the Java runtime. Let me move this out of the way and move this out of the way. If you look at the screen in here, it tells you to change to a schematic. So I'm going to change to a schematic, and it tells me to check values, and it tells me also to pick up a voltmeter, which we will need, and it tells me also to pick up a stopwatch, which we will need. And then what else do we need? We need to make sure that this is in medium. We need to go to advanced and hide the electrons, because it tells us to hide the electrons, and pick up a small resistivity in here for the wires, typical behavior of wires, okay, that there is energy lost or heating. And then immediately stop the play. This is a critical step. So you stop the animation, whatever it does, so that you don't have things start running before you even have the chance to start counting or connecting things or something like that. And then start the clock. The reason why you know it's paused is because the clock right now is not working. So if I start it, you see the clock is working. So I started the play and stopped it. So let me reset back the clock to 0. And this play now is paused because I can start it at this point. I don't want it to start, honestly. So let's pick up what we need to pick up. First of all, we need a battery. So I'm going to put the battery in here. We need the switch. So I'm going to put the switch in here next to it. We need the inductor. So I'm going to pick up the inductor also. We need the resistor. So where is it? Here is the resistor. So we need that. And now we need a bunch of wire to connect everything. So there is one wire connected to this side. And there is another wire connected to this side, and there is another wire connected in here, and there is another wire connected in here, and make sure it's connected. Make sure that this circuit looks neatly organized. Okay. Even if I close my switch now, nothing is going to happen because time is frozen. Okay, so let me pick up the voltmeter and connect it the way it says to connect it. So connecting it to the negative side, and this one connects it to the positive. Before I do that, I'm going to plug in the values that they told me to plug in. Why is this thing not moving now? Okay. It's not giving me zero voltage, is it? There is no current right now. It's not reading a current. That's not good, man. So that is a problem. Can we move this? As long as we don't have a voltage in here, that is a terrible problem, okay? So let me remove the voltmeter. It's not even removed. Cannot even remove it. Okay. When you have a situation like that, it's a good idea. Can we reset everything? Reset all. Yes. Okay. So let me pick up the voltmeter. Hopefully it's not the same stupid voltmeter that was in there, because that's no good, man. Let's see it. Okay, so we have this one. For some reason, it's not picking up any values in here. Okay, let me close this whole thing. Sorry about that. And let me open it again. Okay. And let's hear what happened in here. So again, let me share the screen. Okay. Schematic, show values. Make sure that you have some resistance in here, hide electrons. And let me pick up the stuff in here that I need to pick up again. The switch, the ammeter, the inductor, the battery, the wires, and more wires. Okay, stop the time, pick up the voltmeter, pick up the stopwatch, bring the voltmeter in here and in here. Very good, now we're good. Okay, now we have 0 volts, exactly how it's supposed to be. I'm glad that this happened because you guys will when you run into situations like this one, you know exactly what to do. So again, I need to change this one to 12 volt. They told me to change it to 12 volts. So I'm going to just enter it manually and hit OK. So it's done. When you close it, sometimes it closes. So the only way to go back into it is that's how I found out actually. So click on show and hide values and show them again. That will going to appear. The inductance is 50 henries, which is a huge inductance, by the way. R is 10 ohms, as is, and the EMF is 12 volt battery. And we did all of the things that we're supposed to do. So I'm going to close the switch. Once I close it, nothing happens. The reason why nothing happens at this point is because the time is frozen. And if you look down on the next page, there is a table. And in the table, it has the time, and the time has 10 values, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what I'm going to do now, I'm going to let go of the clock, basically, let go of the time in the bottom in here in the play, and stop it immediately because I know the following. There is a 12 volt right now, voltage across the battery, okay, immediately after I close the switch. There is 0 current in the circuit. Meaning, when there is 0 voltage across the resistor because there is no current through it, because R times 0 is 0. So that means that all of the 12 volt is really here across the inductor. And as time goes by, this voltage will move from here because the current starts to build more and more and more and more, while this inductor is opposing that change. So at the end, the current becomes steady, which means the derivative of a constant with respect to time is becoming 0 at the end. So the voltage drop here becomes 0, and all of the 12 volts should be here. So I know if I let go of the time, that at some point, when I wait long enough, that this voltage approaches 12. It's not going to be exactly 12 because these wires have in them Joule heating also. They have a finite resistivity. So it's not going to be exactly 12. It's going to end up being 11 point something. Okay, depending on how big these things are. Anyway, so I'm going to start the time and stop it immediately and pick up the first values. So start it and stop. I'm sorry, that's bad, okay, because we did not start this thing. We should have really started, okay? Sorry about that. So ignore this value right now. So we start with non-zero value, okay? That's fine. We can start now the time, and this value will be shifted a little. So we're going to start it and stop it. So right now, it's giving me 2.206 volts after 0.48 seconds, okay? Think of the current that is right now running. The resistance is 10, and the voltage is 2.206. That means there is a voltage, there is a current of 2.206 divided by 10, or 0.2206 amps, 220 milliamp. That is how much current is running through the circuit right now. So if I've done everything correct, and if I go to the table, so I'm going to start it again and stop. Then I pick up the time, I mark the time on my table, and I mark also the value of the voltage in here on the table, because on the table, it has a column for the time and a column for the voltage across the resistor. So I'm going to fill those 10 data, provided I did it carefully. I didn't do this mistake in here because I was talking, I forgot about the instructions in here. If you read the instruction, it tells you, make sure the animation is stopped before you start the stopwatch. Okay, so it's stopped. Then start and stop the animation and record the values of the time. So we're going to start the stopwatch and then do this thing in here. Okay. So if you do this 10 times, you're going to get all of your data, the first two columns actually of the data. So assuming that we did that, and let's say, for example, this is another value, this is another value. So at some point, if we wait for a very, very long time, an infinite amount of time, the voltage in here will change very little because it's an exponential growth. Right now, it's at 10 point something volts. So at some point, it's going to slow down because it's going exponentially. So at some point, it's going to reach almost a saturation. So it's still increasing. So this is after 22 seconds. So now it's reaching almost the point where it's not going to grow anymore. Okay, it's hardly increasing now compared to the clock that is still ticking big time. So now 11.5, 11.53 right now, 531. So it's barely now picking up a digit after a long time now. So that means the exponential really has reached the saturation point in here. And the reason why it's not exactly 12 volts is because there is some voltage in the wires in here. As a matter of fact, if you check them, you probably are going to find a slightly bigger. As a matter of fact, there is a voltage across this wire, 0.1 volt right now. So, and that is because of our choice of making it more realistic in here. So the voltage right now, it's 11.535, and the time is changing and we're hardly getting anything. That's why it's very important to pick up the initial values first before it reaches 10 or 11 volts. Okay, try to pick up some values in the beginning around 1, 2 volt, 3 volt, 4 volt. Try to get it so that you don't have, you're not in this situation. Basically, you're waiting for a long time to see any change in the voltage in here. Ultimately, it's going to reach the limit, but there is no saying how long it is. So that is the point of how to build the current. At this point in here in time, which is 92.07 seconds, the voltage in here, there is no change in current, because if there is change in current, this voltage will change. This voltage across the resistor will change. So derivative of I with respect to time is going to be 0, which means that there is no voltage drop across the inductor. So this is basically how you build the current inside the inductor. So let me stop this sharing. Let me go back to the PDF file to see what's going on. So in the PDF file, assuming that we did everything correct, and this here, we have all of this times, which is 10 values, and we have the V's from the voltmeter in here. Then we're going to use this expression. Remember, epsilon is 12, and VR is whatever value in here. So the first one was 1 volt, so be it. I'm going to the calculator and punch in y equals to ln of 1 minus whatever value in here divided by 12. And then do the same thing for all of the others. If you have access to Excel and you can do it in Excel, that would be great. That way you save yourself a lot of time and it gives you X values. The only thing I have to caution you is you have to be mindful of the fact that Excel will give you extra precision, which is not true, which is not correct for our case in here. Anyway, so we have these values, and now we're going to do data fit. This should be a linear function as a function of t, because all this does really is take this expression, V across the resistor, subtract from it this values in here, and RL in here is practically 0. So we took RL to be 0 in our case, so RL is 0. So what you have in here, you have, move this to the other side, you will have epsilon minus V sub r of t is equal to, basically RL is 0 in here, I naught is 0 in the circuit. So it's going to be minus epsilon divided times R naught over R naught. So everything cancels in here. So this is more of an exact expression. So take this expression, basically it's better. Multiplied by R to find VR. So VR now is equal to epsilon plus or minus epsilon times the exponential. Move this VR to this side and move the minus to the other side, becomes a plus. Take the natural log of both sides and you're going to find t is basically equal to some negative value times this natural log of the difference. So basically you need to find an equation that looks like a line, and that line is going down. Okay, so it's slanted. In other words, the slope needs to be negative, and it has to be around negative R over L. Remember R that we started with is 10, and L is 50. So this slope needs to be roughly about negative 10 over 50, or negative 1/5, or negative 0.2. So that is basically the slope that you're looking for. See if it fits this data that you collect from here, y as a function of t, if indeed it has, where y is this natural log, if indeed it has a negative slope of 0.2. If it is, then you're in good shape. If it is off, then you calculate the error and tell me basically. Part of the error you're going to get is coming from those tiny resistance that we accounted for. So instead of doing L, we did actually the wires, and it's the same thing, okay? Which is actually more practical for our case. And actually, we could have changed the value of the inductance, and it does not give me the option to change the value in such a way we will have an internal resistance. So that's the only fix that we have for it, to make the simulation look more realistic. Okay. You need to plot that function, namely y, not v, this function, which should be a line like this one, basically, going like this. This, on this side in here, you're plotting basically the time. And on this side, you're plotting the natural log of 1 minus v sub r over epsilon. So it should be a line like this one, and the slope should be negative 0.2. Make sure you label the x-axis, which is time in seconds, and you label the y-axis, which is a natural log of 1 minus vr over epsilon, and basically put the fit of the equation in here. If you're going to use Excel, which is fine, then make sure that the graph looks neatly and include Excel instead of this graph. So we're done with this part. Now we're going to do the RLC circuit in a similar fashion. The RLC circuit is a little bit complicated because you have now a capacitor in the circuit. So the equation for Kirchhoff's rule is similar. This is how much it is. And this is how it looks like, where epsilon now is just a constant. When we did the lecture, we found that the expression is usually of this form, where there's this exponential of, I know we used alpha in the lecture, but in this case, we're using gamma, which is the same thing. So this term cancels, and when we do calculate for it, this is exactly what we have found in the lecture, except they defined it with a negative sign to begin with. So they defined the negative term in here, sign. Okay, so this is a problem. This cannot be correct. Oh, I'm sorry. That's correct. That is 100% correct. Because instead of taking it blindfolded like we did in lecture, namely saying it's exponential of some alpha t, we took it in here exponential of negative gamma t. So gamma need to be positive. So if it's positive, that is a decay. And it is positive in here because of this factor. Okay. So everything is well. And where this tau plus and this tau minus show that the time constant can be found from the decay constant. So basically, the time constant is just the inverse of these numbers. And you can solve for them to find the expressions in there. Now, this is honestly is going to be, if you can do it, that's fine. If you can't, then ignore it for right now. It's really not an essential part of the lab. So the same thing in here, when the initial conditions at t equal to 0, q is equal to q naught, and I is equal to I naught, obtain an expression for b plus and b minus. Let me stop sharing the screen in here and show you how to do the algebra in there. Share this one in here. So this is q sub t at the end. This is a damped system. We're still doing the lab. So q sub t now is equal to c epsilon, which is a constant, plus b plus exponential of negative gamma plus, I like to write it gamma 1, okay? And I like to write it b1 in here instead of this things in here. Plus, if you want to do this negative signs, that's fine, but it's going to be too many negative signs, it's a little bit confusing. Exponential negative t in here, okay? C is the capacitance. Epsilon is the charge in there, the voltage in there. So what we want in here, we want q sub 0 equal to q naught at t equal to 0. So this is at t equal to 0. That means this is c epsilon. Because again, we're going through the square signal, and times we have a charge, at times we go back on the opposite. So there is an initial charge and there is probably an initial current too. So when we flip, these things change. So plus b1 plus b2. This is because t is equal to 0. So exponential of 0 is 1 and exponential of 0 is 1. So that is basically q naught. I naught, on the other hand, is equal to the derivative of this expression with respect to time. So I need to take the derivative, so that drops a negative gamma 1 times b1 times the exponential of 0, which is 0, minus gamma 2 times B2 times the exponential of that thing equal to 0. So basically, this is the expression that we found, again, at t equal to 0. Remember, I is dq over dt. So I took the derivative. In doing so, I drop in negative gamma 1 and I drop in negative gamma 2. So basically, we have two equations in B1 and B2 to solve. That's all. So these are equations that we should be able to handle. So basically, the first equation says B1 plus B2 is equal to Q naught minus C epsilon. And the second equation says gamma 1 B1 plus gamma 2 B2. Okay, let's put the negative signs in here because we have to go away. So negative minus gamma 1 minus gamma 2 B2 is equal to I naught. Okay, this is how we typically process with this type of equations. We multiply this equation by gamma 2 and add them side by side. When we do that, these terms cancel. So what we're left with is gamma 2 minus gamma 1 when we add them side by side times B1 is equal to Q naught times gamma 2 minus gamma 2 times C epsilon plus I naught. All of these things are the initial conditions. So these things are known. What we want to find is B1. Remember, gamma 1 or gamma plus, that's how it's called in here, is equal to gamma 1 or gamma plus. In the book, it's in the instruction is gamma plus. It's R over 2L plus the square root of R over 2L squared minus 1 over LC. We gave them names. Actually, we gave them lambda. We gave them omega naught to make the writing a little smaller, but we can leave it as that. And gamma 2, or gamma minus in here, it's called. Let me make sure I have the correct order, okay? Yeah, that's correct. So gamma 2, which is gamma minus, is the same thing with the exception I have a minus in there, R over 2L, minus the same stuff, R over 2L, the whole thing squared, minus 1 over LC. If I do that, this difference between them, obviously, this term cancels. That means we're doing gamma 2 minus gamma 1, by the way. It's going to be minus 2 times the square root of R over 2L squared minus 1 over LC. That's all. So that is the difference between them. So if we do that, plug into this expression, we have found B1. So B1 is just this whole number, which has this I naught and Q naught and gamma 2 and gamma 2 in there times C times epsilon. And we do the same thing. We take this equation now for the next step. So this is step 1. Step 2, to find the other value, we can take the first equation and actually multiply it by gamma 1 instead and add them up side by side. If we do that, there will be, this term will have a gamma 1 in it times B1, and this term will have a negative gamma 1 times B1. So they will cancel when I add them up, but they will have gamma 1 minus gamma 2. So we'll have the same thing, except the signs will be different. So we'll have gamma 1 minus gamma 2 is equal to, on one side, I will have gamma 2 times, gamma 1 times Q naught. So it's gamma 1 times Q naught minus, again, gamma 1 times C epsilon naught times FC epsilon. This is times B2, of course. We need B2 in here. Because I took already the sum in here, plus I naught. And I already did this difference. This difference is actually equal to the negative of this difference. This is positive 2 square root of R over 2L squared minus 1 over LC. Divide that, and now I have found by B2. So this is basically the whole calculation for question number 3. Okay, that's why I'm saying this lab is kind of intensive in terms of calculations. You guys need to really get on top of these things. Okay, and this is, think of it as preparation for the exam too, because this is not outside of the lecture. This is just reinforcement of what you guys need to know about this RLC stuff. So this is actually a reinforcement of that. I'm sorry, this is question number 4. This is the question number 4. Question number 5. Using the circuit kit, construct a circuit and a DC power supply of 12 volt, where R is 10 ohms, L is 10 Henry, and the capacitance is 0.05 farads. How long does it take for your circuit to reach its steady state? Okay, so this is going to be the last thing of the animation in here. So I'm going to come back in here, stop sharing the screen in here, and share with you, share the kit in here. So at some point I need to break this. Probably let me remove this one. Remove. So I'm going to bring a capacitor to the circuit. That's all. Okay, that's fine. Put it in there. Now bring a wire. Okay. So this is my RLC circuits, except this value now need to change to, oh, no. This is no good. So let me do the same thing. Delete that thing there. Stop it completely, because we need to start from new values, because we already have a current in the circuit. We have already stuff in the circuit. So we don't want that. We want to start afresh, okay? So it's a good idea to close it and open it again, because that Java thing is very hard to reset. So again, let's do it from the start, which is no big deal. It's just to practice these things. Let me share with you the screen. So again, I need to go to schematic, show values, take the voltmeter, take the stopwatch, make sure this is stopped, and start the clock this time around so that we have that controlled. Show the values in here, make sure I have this one, and hide the electrons. We don't want any electrons. Take a battery, we need the battery. We need a switch, and we need an inductor, and we need the resistor, and we need the capacitor. Okay, and okay, and what else do we need? A bunch of wires. This wire, no, there. This wire, this wire, and this wire in here. Now we can safely close the circuit because we have the time is stopped, so we don't have to worry about that. And we're going to bring the voltmeter and start reading the voltage across the resistor. We're not going to run into the same problem, are we? The same problem. I sort of don't like that now anymore. Sorry about that. Okay. So again, we need to have this controlled now. We can't really. That's why if we did it in the lab, you wouldn't be running into this situation, because you will have it working. So let me share again. Okay, so let me pick up the stuff first. Let me, no, I don't want the electrons to be showing. Show, remove electrons, put some finite value in here, and pick up this time watch, stop this one, start the time, and let me pick up the voltmeter at the end, okay? So this one, that's fine. You can connect them, it will be clear. And this one now, the wires, fine. And the okay. And there is another wire in here. And finally another wire in here. Okay, pick up the voltmeter now. We need a 0 voltage. If we can get a 0 voltage. Why is this doing that? How about if we can pick it up in here, can we? There's something in here with this voltmeter in here. How about an ammeter? Can we get an ammeter? Let's see here. We do it with the ammeter. How's that? I mean, we're changing the stuff, so hopefully you guys don't. So let's see here if the ammeter will give me any reading for the current, because it's the same thing, really. That's what I want to see, is the current stabilized at the end, more or less. Okay. Oh. Now this whole thing is not working correctly now. Is it my computer or is it the animation? I don't know. Hold on. If you have difficulty with it, please let me know, okay? I know I'm having difficulty with that right now.
So far, it's good on my screen.
Okay, so if you get it working, that's fine. If not, I'm afraid some of your other classmates will have difficulty with it. So let me find it again. I've lost the track of what my file is now. Okay. No big deal. I'm going to find it in here. So let me go back. Let me go back to PHY4B and let me pick up the file. Minimize this, don't close it. Minimize this, and share the screen. Hopefully it's not the share that is causing this one. So let me see if I can get it going without the share, because I need the resistor somehow. And I need the voltmeter to give me 0 volts across its ends, okay? When I start without any current in it. So that's basically the problem right now. Okay, I got it going. So let me share now. It's probably a good idea to put if you're into a similar situation, to put it by itself first, okay, and then start adding elements to it. So it's fine now. Add the farads, add this guy in here. That's fine. Connect them is fine. Now it is my power supply. Here is my power supply, and here is my switch, and here is my wires. Now a bunch of wires. And even the wire at the end was not working for me. Couldn't even get wires to connect. Okay. Okay, I need to stop the time. Good. And I need to add stopwatch. And I need to start the stopwatch. I can close the circuit. But before I close the circuit, now we need to put the values. This one needs to be 12 volt. So we need to make this one 12 volt. Not 112, 12 volts. That's good, done. Check the value again to make sure it's 10 volt. So we need the R to be 10 ohms, and it is 10 ohms. The L to be 10 ohms, so I need to tell Henry, so 10 Henry, so I need to change this value to 10. Okay. And the capacitance needs to be 0.05, so I'm going to change the value in here and make sure it's 0.05. And it's done. And let's make sure that everything is exactly how it's supposed to be. Now, it's safe to close the switch because there is nothing happening in here, okay? So, the time characteristic in here, exponential of negative, how much? R over 2L. So it's going to be a few seconds, basically, of time characteristic. You can do the math for it. But the time characteristic doesn't really kill the current right away. It gives it several values of tau. So about 10, 20 seconds, this should die out. Should stabilize. So right now the current, the voltage of the current are changing from a positive value to a negative value. And it's 7 seconds. So at some point there should be no changes or hardly any changes. At this point, I can safely say that it has stabilized, okay? Because hardly there is any change in it. It was oscillating back and forth, and now it's basically damped enough so that there is no more oscillations. So this is basically the question. That's what you're supposed to do for question 5. So at this point, we're done really with the Java. So let's go back into the instructions. And now we're doing the Lrc the resonance. Basically, the power supply is a I'm going to close the Java. We really don't need it anymore. This circuit, RLC, with the power supply that is V0 cosine omega t. So the Vmax in this case is V0. And the frequency of the circuit is omega, the driving force. So if we do Kirchhoff's rule, this is basically what we end up with. And now we define the reactance of the inductor, which is XL equals to omega L, and XC is 1 over omega C. And R is R, basically. So the impedance in this case, Z, is the square root of R squared times XL minus XC squared. Remember, XL is omega L and XC is 1 over omega C. And phi is the arctangent. Basically, the tangent of phi is XL minus XC over R. So this we saw it in lecture. So Q sub T now because this is basically what the voltage is. So Q sub T is some phase shifted value from this value in here, and the current is exactly going to be in sync with it. So at this point, we have the values that we have in here. So VC will be Q over C. So it's this number over C. And if you divide this by C, you will have 1 over omega C, which is XC. So it's V naught XC over Z, and VR is V naught, because you have to just multiply this one by R. So it's going to be R times V naught times dQ over dt. I'm sorry, take the derivative of this guy in here. So the omega cancels the omega, and you will have V naught over Z times R. So it's going to be R over Z times V naught times the sign becomes a cosine when you take the derivative. And finally, VL, this is not correct. This is not, there is a Z in here, not, please correct this expression in here. This is not correct. Because when you take the derivative with respect to omega, the omega cancels and the sign becomes a cosine, and the denominator will be a Z in it, not an omega. So the omega cancels, not the Z cancels when you take the derivative. So this will be, please fix that, okay? Anyway, V sub L is L times the derivative of the current with respect to time, which is the second derivative with respect to of Q with respect to time. So basically, this expression now, when you take its second derivative, there will be another omega that comes out times L. That's going to be XL. And the derivative of the sign is a cosine, and the derivative of a cosine is a negative sign. That's where the negative is coming from. And that is basically the expression that you have in here. So show algebraically that VL plus VR plus VC is equal to V naught cosine omega t. So let me share with you the screen in here. Let me stop screen in here and share with you what this means. Where is my... I lost that page in here. Let me find it. Here it is. So this is what we have in this expression. We have VL basically. Oops, I don't mean to write in here. There's a bunch of writing already. Let me pick up a different color in here. Pick up the blue in here. So what we have in this expression is we have VL, according to that expression, is equal to negative V naught over Z times XL times a sine omega t minus phi, correct? And VC or VR is equal to positive V naught over Z times R times a cosine of omega t minus phi. And then we have VC is equal to Q, which is equal to V naught over Z times XC times the sine of omega t minus phi. And don't forget the values of XL. XL is simply omega L. XC is simply 1 over omega C. And Z is the square root of R squared plus XL minus XC squared. And the tangent of phi is equal to tan of phi is XL minus XC over R, which means that the cosine, if you look at the trick that we looked at it the other day, so this will be R, this morning actually, this is XL minus XC, the difference between the two, and this is Z actually. So the cosine of phi is simply R over Z, okay? Cosine of phi is R over Z. Okay, it's very easy to prove actually from this expression too. Since you have the tangent and the cosine are related to one another, because the cosine is equal to, what is it? 1 plus tan squared of phi is equal to 1 over cos squared of phi. From here, you can find cos squared or cos phi, 1 over square root of 1 plus tan squared of phi. Since you have this expression for tangent, you sub in there, and you're going to find the same expression here for the for the cosine. It's R over Z basically, and a sine of phi will simply be equal XL minus XC over Z. So in here it's R over Z. Having these expressions in here, can we check that VL plus VR plus VC is equal to V naught cosine of omega t? That is what we're supposed to check. Now remember, VL is this whole thing, negative V naught times the cos of the difference. And the cos of the difference is cos plus sin. That is a trig identity. The cos of the difference, now the sign of the difference in here. The sign of the difference is sine of omega t times cosine of phi. So, and minus cos of omega t plus sine of phi. So that is basically what we need to do. So we have minus V naught times XL over Z times open parentheses, which is cos phi times sine of omega t minus sine of phi cos of omega t. Okay, that's one term. There's this term only, plus V naught times R over Z, open parentheses. I have a cos of the difference. The trig identity said cos of something minus cos something is cos plus sin. So this will be cos phi cos omega t plus sine of phi sine of omega t. And the last expression that I need to worry about is VC. VC is V naught times XC, which is a positive number, positive V naught XC over Z, open parentheses. Again, is similar to the first one, except, yeah, it's exactly because it's a sign of the difference, which is exactly the first term. So it's going to be cos phi sine omega t minus sine of phi cos of omega t. I have to get there all the terms that involve the cosine and the terms that involve the sine. So I have a cos here. I mean, I have a sine of omega t here. I have a sine of omega t here, and I have a sine of omega t here. So I'd like to have everything multiplying by sine of omega t to be 0. And that needs to be 0 because I really don't have a sine omega t in here. So that needs to cancel. And I have a cos of omega t in here, and a cos of omega t here, and cos of omega t here. That needs to be exactly V naught when everything is said and done. So let's get everything that is multiplying sine omega t. So I'm going to write sine omega t in here and expect that everything cancels. On one side, I have negative V naught XL times Z times cosine of phi. Remember, cosine of phi is R over Z. So I will have minus. Since I have V naught, and I have V naught, and I have V naught, so I'm going to pull out the V naught as a common factor. So I'm going to be left with a minus XL over Z times cosine of phi. And cosine of phi is R over Z. So it's going to be minus XL times R over Z squared, basically. Okay? In here, I have an R over Z times sine of phi. And sine of phi is all of these things. So it's going to be plus R over Z times sine of phi, which is XL minus XC over Z. That takes care of this term now. That has the sine omega t. Now this term has also sine omega t times cosine of phi. So I'm going to have the V naught is out. So it's going to be plus XC over Z times cosine of phi. And cosine of phi is R over Z. So this term must cancel. And it is. Because look at these two terms. This is XL times R divided by Z squared. And this is XL times R divided by Z squared. So these terms, they cancel. And this term is also XC times R divided by Z squared. And I have XC times R divided by Z squared, except this one is negative and that is positive. So they cancel. Indeed, there is no sign in the answer. So the terms cancel in here for the sign. I need to gather the stuff that has to do with the cosine. So I'm going to do the same thing. I'm going to pull out V naught times cosine of omega t. And this term better be 1. When I add them up, they need to be 1. So what I have in here, I have a negative times a negative is going to be positive. So I have a positive XL over Z. Here is XL over Z times sine of phi, and sine of phi is XL minus XC divided by Z. So I took care already of these terms. Plus times a plus. So it's just this term now, because this is the one, the cosine omega t that I need. So plus R over Z times cosine of phi. And cosine of phi is also R over Z. So this is R over Z times cosine of phi, which is R over Z. Okay. The last term that has a cosine in it is X over C minus sine of phi. So it's going to be a minus XC over Z times sine of phi. And sine of phi is XL minus XC. So this is XL minus XC, and the whole thing is divided by Z. Let's check if this number is exactly 1. It needs to be 1. So I have R times R, that's R squared divided by Z squared. So this term in here is R squared over Z squared. Plus, as a matter of fact, I have Z squared in the denominator everywhere. So I could take it as a common denominator. So I have an XL times XL, that is XL squared, minus XL times XC, that's minus XC, divided by Z squared. I mean, XL times XC, that's XL times XC divided by Z squared, correct? And plus, again, in here, the common denominator is actually Z squared, that is popping up everywhere. I have XL times XC, that's negative XL times XC. I have a minus times minus, that's plus XC squared. And now that is under the parentheses. The common denominator is clearly Z squared, so I'm going to put it in the denominator. And in here, what I have R squared plus XL squared minus 2 of them, XL times XC, plus XC squared. Well, this is just the square. This is the square. This is just the square expanded of XL minus XC. This 2 terms is XL squared plus XC squared minus 2XL times XC. That is nothing but XL minus XC squared divided by Z squared. Remind you that the Z squared is actually, I mean, Z by itself is the square root of this thing. So when you square it, it's just going to be R squared plus XL minus XC squared. So indeed, this is 1. 1 times V naught cosine omega t. So it checks. So the other side is V naught cosine omega t times 1. That's all. So I know it's a long derivation, but I'm hoping that you guys can go through this calculation and be satisfied, be happy that this is indeed true. Okay. So I'm going to leave it to you guys. So if you have difficulty with it, please come back to this recording and look at it. So let me go back into the lab instructions. So this answers this question actually. So please append to it an attachment for this question. So we have VC is equal to V naught times XC over Z. So those are the maximum values coming from those equations. Now take values of L equals to 10 millihenry, R equals to 5 ohms. How long are we been doing this now? How long is this recording? Oh man, it's an hour already. Okay, it's a long lab. So L is 10 millihenry, 10 times 10 to the negative 3, that's what that is, or 0.01 Henry. R equals to 5 ohms, and C equals to 100 times 10 to the negative 6 farads, and V naught is equal to 10 volt, okay? So this is what we're doing in here. So we have an oscilloscope, assume that you have an oscilloscope, and that oscilloscope is set up for this circuit, okay? With a voltage power supply of 10 volt, okay? And the omega of the power supply is variable. It can be 500 radians per second or another value. So if it is 500 radians per second, find XL, find XC, find Z, find phi, find VC, find VR, find VL. It's easy because XL would be just 500, which is omega, times 0.01 Henry. So you do the math, okay? That's going to be how many ohms you have in here. 500 times 0.01 should be 5 ohms. Okay, so that's how much XL should be. XC. XC should be in this case, where is C? It's 1 over 500 times 100 times 10 to the negative 6. So it's going to be a big number. Because remember, you have to take 1 divided by 100 times 10 to the negative 6 in the denominator, and also in the denominator 500 multiplying that, because xc is 1 over omega times c. Just to remind you, the expression for it, here it is. xc is 1 over omega c. And you have omega and you have c. So this is easy. This is straightforward. And z, you have r, which is 5 ohms. So it's going to be square root of 25 squared plus whatever the difference between xl and xc squared. And that is going to be z. Phi is going to be the difference between xl and xc that you calculated, divided by r, which is 5. And you do the arc tangent. Make sure your calculator is set up on the proper mode. So if it is in degrees, you report the answer in degrees, okay? VC is clearly equal to 10 volts times the ratio of XC over Z, whatever you find from Z. VR is the ratio of the 5 ohms divided by Z, whichever you found in here, and that is going to be your VR. VL is the same thing. It's going to be XL that you calculated in here, divided by Z that you calculated in here, and times 10 volts, and that should be the answer to it. So this is straightforward, okay? Take these values that you found in here and go to page 12. Let me find page 12. And report this data in this entire row. This is a theory. This is the one that you calculated by theory, okay? Now, we go back to page 9 where we were. Okay. So we did question 7, which is we're going to need question 7. And then you're given this chart now. Okay. This is what the oscilloscope gave you. So you need to print this picture and use a ruler to do the following measurements, which are critical in here. 5 divisions in here, which is from this dark line to this dark line, is, 1 division from dark line to dark line is 5 milliseconds. That means this is 1 millisecond, this is 1 millisecond, this is 1 millisecond, and this is 1 millisecond for a total of 5. 1, 2, 3, 1, 2, 3, 4, 5 milliseconds. Okay, so you have 1 division, 2 division, 3 division, 4 division, 5 divisions in here. So you have 25 milliseconds from edge to edge. In here, you have several pictures of different stuff that is listed in here for you. You have the power supply. 1 division in here is 20 volt. That means from here to here is 20 volt. That means midway somewhere is 10 volt. And the power supply, they tell you it's 10 volt. That's exactly what the calculation is. So if you answer the question step by step, it tells you to measure from top to bottom, and here it should be 10 volt. You measure the period from this 0 to this 0, it should be how many milliseconds? That's going to be the period. You invert the period, that's going to be the frequency, and you multiply it by 2 pi, it should be 500, or around 500. When I did it, it was 502. So now we have found omega, to make sure that omega is correct. This, you need to find the amplitude in the capacitor and answer the question. Because remember, you calculated VC. You calculated VC. Now you can measure VC by just going from either from where it's 0 to the maximum. How many divisions you have? 1, 2, 3, 4, slightly more than 4. Remember, this from here to here is 20. From here to here is 20. So this must be 5, 10. No, what is it? From here, 1. Wait a minute, let me count them again, okay? 1, 2, 3, 4, 5. And that is 20. So that must be 4 volts only. So from here to here is 4 volts, 8 volts, 12 volts, 16 volts, maybe 17 volts, okay? So that's the value that needs to go here. Use the ruler for it, okay? You're going to compare these two values and tell me what the error is. Are they similar or are they different? And you do the same thing for VR, and you do the same thing for VL. You see how many divisions? From when it's 0 to the maximum. It's barely less than 4 volts, actually. Probably 3.5 volts or 3 volts or something like that. So that, using the ruler, you're going to tell me how much VR is, VSC is, and VL is. Then now comes the hard part of finding what Z is, what XL is, and what XC is. If you solve these equations backward, let me go back into the equations. Actually, it tells you in here. So XC, because you measured VC and you measured V naught, okay? And you have the value of Z, you can find what XC is, okay? You can find what the value of XR is, and you can find what the value, I mean, knowing R, I'm sorry. R is fixed, 5 ohms. So you can do the ratio of VC over VR. It should be basically the ratio of, or find Z from here, and plug it into the other equation and basically get rid of the Z and use it in terms of R. So what is the expression that we're supposed to be using? Hold on. Because R is fixed, you measure it from questions 5 and R is equal to 5, you calculate XL. Okay, here is the deal. XL, if you do that, is R times VL over VR. So R is 5 ohms. So VL, you measured it. Here is the measured value. And VR, you measured it. Take the ratio multiplied by 5, and it's going to be XL. And you do the same thing for XC and the same thing for Z, basically. Here is the formula that you're supposed to be using. This is a measured value. This is a measured value that gives me XL. This is a measured value for VC, and this is a measured value for VR. Multiplied by 5, it should give me XC. This is the measured value for V naught from the table. Here is V naught that you measured, by the way, from the chart. Oh, where is the chart? I'm sorry. Here. You measured with a ruler. This is V naught. And you measured what VR is. It's this value, divide by 2, divide by each other, basically. And you multiply by V naught, by R, and you should be able to find how much Z is. Now, basically, you fill out this side now, okay? Now, you take VL minus VC divided by VR, and you're going to find the arctangent of that, and that's going to be your measured value of 5. Because all of this data is measured now. And you're going to compare side by side and tell me if there is an agreement or disagreement between the data. That is, in a nutshell, what you're doing. The last step of this lab is actually to draw these graphs for 2 different values of omega. And the values of omega have have changed a little. And the numbers are still the same, but the values of omega is 1200 radians per second. And you do the calculation. This is basically a typical calculation of how you find. Here is a question. Do the same thing in here that we did before, except omega is 500, and now you draw the graph similar to the other one. So you're going to calculate those values. You already did calculate them. So you're going to draw in here a distance that is equivalent to 5 ohms. How much you're going to decide. If this is 5, that's fine. Then you have a value for omega L, which is XL, and you have a value for XC, and you're going to plot the difference between them, which is going to be here, and you plot the line in here, that's going to be Z. So you're going to verify the same expression graphically now. Remember, this stuff is important for your exam too. This is not just for a lab. This is extremely important for your exam. You need to understand these things, okay? And you redo the same calculations in here. So basically, you have done that. Now, do you have any, for omega equal to 5, do you have a more capacitive or inductive? So basically, depending on XL and XC, which one is bigger? If XL is bigger than XC, it's an inductive. If XC is bigger than XL, this is, in this case, a capacitive. That's all, okay? Okay, the last part, data analysis. You're given a bunch of data in here. You're given omega that changes from 100 all the way to 10,000 radians per second. And in doing so, you're given VC changing from 10 volts back to 0.0. So it's going from small values, increasing up to 20, and then decreasing again. VR is basically increasing up to 10 and then decreasing again. VL is increasing again and then decreasing again from that 20 value. Okay, and the phase now goes from almost negative 90 degrees to positive 90 degrees, basically. So we're doing this graphing here. So you're going to graph this function now, phi, as a function of omega, except it's not omega, it's the log of omega. So this is a log scale on this terms of omega. Because if you do it in terms of the plane omega, the graph will be very, very big. Because varying from 100 to 10,000, it's going to be ridiculous. So you do it with a log. So taking the log in here and drawing this one, and that is basically a semi-log that is properly scaled on the last pages in here after the conclusion page. Okay, so this is VC, this is VR, this is VL, and this is phi. This is the phi that I was talking about. It should be something like this. At around the resonance frequency, it should go back to 0. And where is the resonance for this circuit? It should be when the voltages are maxed. One of them is out of phase with the other. And basically at that point, let me go back to the data. So this value is actually the resonance value in here. The phase is exactly 0 in this case. They're out of phase. I mean, that is actually in sync. So in this case, this is 20 volt, cancels this 20 volt. And the only thing that is left is the voltage across the resistor, because this one is on one side and the other one is the other side. And the low frequencies, the circuit is more inductive because omega is very tiny. This one is going to be negligible. In a very high frequency mode, omega times L is bigger than 1 over omega times. So the circuit is actually going to be inductive at high frequencies. So this answers all of your questions. Hopefully you go through these questions and answer them. They're all related to this lab. And if you look at the actual resonance in here, it's going to be around 600. No, for this data is different in here. So it's going to be around this 1000, okay? So this is data that was given to you. Somebody collected it for you and basically placed it in there for you. Okay. This lab is long and it's painful and it's dragging. So hopefully you guys can go through it. And if you have any difficulty with it, please let me know. Make sure you include these graphs. Excel can do also logarithmic scales graphs, semi-logarithmic, because this is a logarithm in here and this is linear on that side, okay? Sounds good? I'm not saying it's straightforward. I'm saying it requires a lot of work. You have until the 29th to take care of this one, which means you have to start, guys, right away on it. Okay?
Yeah, this is going to be a lot of work in the last one.
Okay. I hope that you...
We'll manage. We'll all manage.
Okay, very good. So I'm going to stop sharing and stop recording. And this is one of the longest labs, so I'm going to post it shortly, hopefully, for the people who are not here to watch it. I know Byron said that he's going to join us and some other people later on, but I'm going to post it for them anyway. Thank you.